is a paired t-test. Okay, so if you're following along with me, I have the slides that I normally put up right over here on the left side of my screen, and then I have your notes that I give you on the right side of my screen. So I'm going to be typing in those, writing in those, so you can follow along with me. Okay, so paired t-tests are typically used when you are trying to compare two things, right? You get a lot more information when comparing two sets of data rather than just running like a one sample test or doing a one sample interval. You get a little bit more information when you're doing comparative studies. So there are two ways that you can do comparative studies. The one that we're going to focus on in this video is the paired t-tests. Okay, so we use a paired t-test in two different scenarios. Okay, so we use a paired t-test when, I'm over here struggling with my typing, when, I'm really over here struggling with my typing. Oh my goodness. Okay, so you typically use a paired t-test when either you have one subject that receives both treatments in a study, or when treatments are easily paired. Paired for different subjects. Okay, so here's what I mean by that. Okay, if you think about one person receiving both treatments, right, sometimes that'll be maybe, it's very typical in medicinal studies where they'll be given a placebo maybe for the first half, and then the actual drug for the second half, right? So the pair is you, right, or the person in the study, right? And there's other ways that you can easily pair different treatments, right? So maybe you're testing something about two siblings in a family, or maybe two products in a particular grocery store, right? They can be paired by store, okay? So those are paired t-tests. The other type of comparative study is a two-sample t-test, right? And you use those typically when you can't pair things. So the way that we define this is that you're going to use these when groups are formed using a completely randomized design. Definitely spelled that one wrong. Whoops. Okay. So the way that we carry out a paired t-test is you find the difference, not different, difference. Okay. Find the difference between each pairing and run a one sample test on the difference column. Okay. And then we write these paired hypotheses, which I'm hoping you already know because we did talk about this. Okay, but we write these in terms of mu sub d. Okay, so mu sub d right there, which is the difference in means. Okay, right. So that's the way that you'll write your hypotheses. All right. So let's go through this example here. Whoops, I went a little too far there. Sorry, everybody. Okay, so we're going to look at this first example here that we did do in class, but I do want to go over it for you again. Okay, so we're still doing a test. This is phantoms, right? So we're still doing a test. Okay, but the test here we're going to run on this column. This one right here, the difference column, okay, rather than running it with these two individual columns, right? Okay, so when you're given data like this, you're going to want to enter it into a calculator. Okay, so I'm going to shift my screen over really quickly. Whoops, y'all can see that I was watching a podcast. Okay, so this is my data right here, or this is my calculator simulator. So I'm going to go ahead and add in a new document. So I'm going to press Control Doc, and I'm going to add a list and spreadsheet, and then I just want to enter this data. Okay, and I have it next to me here. So you will probably, like when you do this, obviously you'll have it next to you when you're doing this. Whoop. Okay, so what I'm going to do is I'm going to enter this data here, and then I'm going to run one variable statistics on it. Okay, I'm going to have to do that in order to get the mean and the standard deviation, which you have to have in order to run a test on anything, right? You absolutely have to have those values. Okay, so I'm going to go ahead and enter my values here. So 11. And if you have the calculator simulator set up at home, you can follow along with me as you do this, right? Or as I do it. Whoops, entered that one too many times. Didn't mean to do that. I'm losing track of my data here. Okay, so 6, 3, 13, 1, and -1. Okay, so that's my data. And then what I really need to do is run some one variable statistics on it. Okay, so I'm just going to go back up to the top. Okay, I'm going to press Menu, Statistics, Stat Calculations, and I'm going to run this one right here, one variable statistics. I've got one list, okay, and my X list is that A column. Frequency list can stay the same. Everything else stays the same, and I'm just going to press OK. All right, so now I have the information that I need. Okay, so we're going to record that later, but that's my information. There's my X bar, and then I'm going to scroll down, and this is my standard deviation right here. You want this one, the one that says SX, not this one. Okay, they are a little bit different. This is the one that we want to use because this is for a sample, right? This would be if this was a population. So this is the one you want, SX. Okay, so I'm going to go back over to my notes here. Okay, and I'm going to write these out. Okay, and I have most of it over to the side for you on the actual on the actual presentation. Okay, so here, this is about caffeine, right? So my parameter here is that we are estimating true mean difference. Then I'm going to put placebo minus caffeine, just so that the AP readers know and so that I know what I actually subtracted. Okay, they do give you points for that on the AP test, so usually a good idea to do. Okay, so it says we're estimating the true mean difference in, and then what they're measuring here is what they're calling a depression score. Okay, all right, then I have my hypotheses. Okay, so these I'm going to switch over and actually write these by hand because it's a little difficult to type sometimes. Okay, so for these, I have HO. Okay, and HO is, remember, in terms of mu sub D. Okay, and it's always going to be equal to 0 here. Okay, that's my status quo, right? I'm assuming that the difference is 0, and I'm trying to prove otherwise. Okay, so my alternate hypothesis here is that mu sub D is greater than 0. Okay, if you go back into the problem, we're trying to see if caffeine gives you a lower depression score, right? So we would think the placebo would be higher. So we're hoping that the difference is greater than 0 here. Okay, all right, so those are my hypotheses. A is my assumptions. So the first thing I want to check is the randomness. And this is not a simple random sample, right? But they did say that this is a randomized experiment. So simple random sample or randomized experiment count here for dealing with the randomness condition. Okay, so you can say that randomized experiment, okay, stated in problem. Okay, then I have my 10% condition comes next. Okay, so that's the one, remember, where you take 10 and you multiply it by the sample size, and the sample size here is 11, right? Because there's 11 people in this study. So 10 times 11, which is equal to 110, and that's definitely less than, we would say, the total number of possible subjects. Remember that you're saying that it's less than the total population, right? So this is the total population for possible subjects. Okay, and then my last condition here is my success fail condition. So remember, for means, you don't have to do the NP and the N1 minus P thing. There's nothing to check here other than sample size. Remember, so we want to check to see either if the population is normal or if the sample size is big enough, right? So the big enough marker is 30 people, right? They just decided 30 after many, many trials. 30 is big enough. Okay, here, but n equals 11 here, which is less than 30. Okay, so you have to check the sample to make sure that there's no outliers or skew. And just trust me on this one, there's no outliers or skew. I checked it. Right? Okay, so you would say the sample size is less than 30, but the distribution, the sample has no obvious outliers or skew. Okay, so those are my three conditions there. Okay, all right, next I need to name the test. This is the easiest one. Okay, this is like 100% the easiest one. These are always just called paired t-test. Okay, easy peasy. Okay, that's what that one's called. All right, next comes my test statistic. Okay, so remember, my test statistic is the X bar value, which we got from the calculator, minus the mean that you stated in your hypotheses, divided by the standard deviation. But you have to calculate the new standard deviation. Okay, so I'm gonna actually, again, write these out because sometimes they're easier to write out. Okay, so I know that my mu is 0, because that's what it says in my hypotheses. And from my calculator, I know that X bar is equal to 7.36. Okay, I got that directly from the calculator. Okay, and then next we have to calculate our new standard deviation, right, or standard error. Okay, so remember the formula for that, and I'm going to write it over here. The standard error formula is the standard deviation of the sample, so Sx, which again you get from the calculator, divided by the square root of n. Okay, so here my standard error is, so from the calculator I got that Sx was 6.918, and then I'm going to divide that by the square root of 11, because that was my sample size. And so when I plug all that into the calculator, I get 2.086. Okay, so that's my standard deviation. And then the last thing I need to make sure I set for myself is the degrees of freedom. Okay, because I'll need that for my calculator. So degrees of freedom is always the sample size minus 1. So 11 minus 1, which is 10 in this case. Okay, all right, so then finally I need to calculate my actual test statistic. Okay, so T is equal to, it's mu, right, and X bar. So I'm going to take X bar, so 7.36, minus mu, so minus 0, divided by that new standard deviation. So this one right here, okay, and that's 2.086. Okay, I'm going to say, figure out what that is, right? I'll plug that into my calculator, and I get 3.529. Okay, so that's my test statistic. So this is the value that I'm plugging into my calculator, okay, on the O step. All right. Okay, so that's the test statistic. That's where most of the math is that you have to do. Once you're at that point, the calculator will do pretty much the rest of the work for you, which is lovely. Okay, so now I'm at my O step, which is to obtain the p-value. So for this one, remember, whenever you're obtaining your p-value, you have to write the probability notation. Okay, so it's the probability that we're saying, what's the probability that we get a difference that's this extreme, right, from the sample? So that's this extreme or more extreme. Okay, so you can either write this Or you can just write it with the t, right? Either one is fine. So we're finding the probability that, what's the probability that I get a t value that's greater than 3.529. Okay, and then once you get here, you got to just plug this into a calculator. Okay, so I'm going to switch back over to my calculator here. Okay, so here's my calculator. I'm going to go back just to a regular calculator screen. Okay, and this is a t distribution, so we're going to run TCDF. So I'm going to say menu, statistics, I want distributions, and then this is the one I want right here, TCDF. Okay, so I'm going to click on that. It's going to give you a lower bound, upper bound, and degrees of freedom. Okay, so if we go back really quickly over here to what we're actually doing, we're seeing if t is greater than something, right? So if you actually sketch this out, whoops, that one's not very good. Really bad straight line. Let's erase that. Try that one more time. Okay, so if I draw out what's happening here, right, if I have this on my lovely normal curve, my boundary is here. So this is my t value, and I'm saying, is it greater than that? So I'm going to shade this way, which means t is my lower bound. Okay, so when I go back, right, when I go back over here for lower bound, I'm going to type that t value. Okay, which was 3.529. Okay, and then my upper bound, I'm just going to type a bunch of nines. Okay, then the very last thing is degrees of freedom, and that was 10. And I'm going to click OK, and it's going to give me this value. Okay, so that right there is your p-value. That's your probability. Okay, so 0.0027. Okay, so I'm going to come back over here and write that out. I got 0. Let me scroll just a little bit here. 0. Sorry guys, I'm still kind of getting a hang of this like screencast stuff. Okay, so here this was 0.0027, which is less than any alpha value we could imagine setting. Okay, so then we're at our M step. Okay, so we're lastly here at our M step. Okay, which is because the p-value is less than alpha, which I realize I didn't actually set at the beginning. Whoops. But here we would set it as 0.05 because they didn't give us one. So since my p-value is less than alpha, I'm going to reject the null. Okay, so your very last step is to state your conclusion in context. So this is the one where you have remember your word formula? Okay, so we say because the p-value is less than alpha, okay, we reject the null. Okay, and then you say there is enough evidence to support and I'm going to just type it out in words here. So to support, you could say HA, or you could call it the alternate hypothesis. And then you say which states that the true mean difference in depression scores is greater than 0. Okay, essentially meaning that yes, the caffeine did help, right? It did reduce the depression score, which is good. That's what they wanted. Okay. And then one other thing I want to point out to you here is that this is an experiment. So a really common thing that they like to do with problems like this, especially that involve experiments, is they ask you afterwards, okay, so what can I actually conclude? Like what inferences can I make? Okay, so we can't say anything about the population here because these people, I think, were volunteers. If you go back and read the actual scenario, that these people were volunteers, right? These subjects are volunteers. So I can't extrapolate about the whole population of people to say that this drug would work or the caffeine would lower depression for everybody. But I can say that there's a cause and effect relationship here, right? That me giving them this pill did lower depression for this group of people. Okay. All right. So I'm going to go ahead and pause this for a second so that I can get to the next problem. Okay, but the next one is another paired t-test. So I want you to try it on your own if you can. So go ahead and pause the video here and then see if you can figure that one out. Okay, see if you can figure that one out. And then unpause and kind of check your work with me because I'm going to do that one with you as well. All right, so here we are at the next paired t-test problem. So on yours, you won't have this difference column filled in. I went ahead and filled it in because I needed to do that, right? All of our tests, our paired t-tests are run on that column, the difference column, right? Neither of these other ones. So this scenario for this problem is about grocery lanes. So these girls are trying to figure out if in general, the express lane is faster than the regular lane and actually try to prove it, right? So the numbers that you have on your screen are times that it took in seconds to get through these lanes. And they did a bunch of stuff to add control to the experiment, right? Like they both went through at this exact same time, right? With the same number of items, the same type of items, right? To get rid of any confounding variables there. Okay, so negative numbers really are what you want here because they did express minus regular. So if the express lane is faster, we would expect these numbers to be negative, right? So in this third one, for example, my express lane took longer than the regular lane. Okay, so very first thing that you want to do once you get this, even before starting the test, is go ahead and enter the data into a calculator and run one variable statistics on it. Okay, so I already have my data entered here in my calculator. Okay, so, and then I named it GS for grocery store. Usually a good idea to name these, remember, right? Because it's a lot easier to pick out the column that you want. Okay, so I'm going to take over here, I'm going to press menu, and then I'm going to look at statistics. Okay. My God, sorry, stat calculations, and I'm running one variable statistics. Okay. I only have one list, and my X list, if I click this down arrow right here, GS is what I'm looking for grocery store. Okay. So once I have that, everything else stays the same. I'm going to press OK. And here is my data, right? So I have my X bar, which I actually think I may have entered one of these wrong. So give me 1 second. I have to pause the video real quick because I think I entered one of my data points wrong, which is causing all of my numbers to be wrong. One moment, please. Okay, everybody. So I figured out what the issue was. I actually entered everything correctly. Problem was in my original data, when I did this the first time, I had one value that was incorrect. Not exactly sure where I got that number from because it's completely wrong. So in any case, I'm human. It happens, right? Okay, so let's go ahead and run this paired t-test. Okay, so here I'm not going to be able to write and type everything out just because the way that this is. So some of this you're going to have to tolerate my crappy handwriting. Okay, so I'm not going to rewrite the parameter part because it's already here for you. So here for parameter, we're estimating the true mean difference in time to go through these lanes, right? So when I wrote it, time required to purchase items at the supermarket, okay? And I did express minus regular, okay? So next, right, I'm gonna look at my hypotheses. So my H step, okay, right, my H step, whoop. Okay, so I have two hypotheses here, right? So I have HO, whoop, sorry guys, I'm struggling a little bit with this mouse. Eventually I will get the hang of it. Okay, all right, so for my H step here, okay, I have two hypotheses, right? So my null hypothesis, remember, is always that the difference is zero, right? That's my status quo, right? Right, so mu sub d equals 0, but here my alternate hypothesis is going to be a little bit different, right? So it's not going to be mu sub d is greater than 0. It's actually mu sub d is less than 0 here, right? Because remember, we want the express lane to be faster, right? So if the express lane is faster, then subtracting the express and the regular should give me a negative number. So that's what I'm hoping that I'll find. Okay, all right. So those are my hypotheses. Again, I'm not going to write out all of the assumptions because I have them for you right here. Okay, on this slide. So again, you have your 3 conditions, right? So randomness, not a simple random sample, but they did say that this was a randomized experiment. So we're fine there. Okay, my sample size here is 15. If you go through and count, I think they also set it up in the problem that there were 15 times that these 2 girls went through the supermarket lanes. So 10 times 15 is 150, which is less than the total number of possible store visits. Okay, and then last, your 3rd condition is your success-fail condition. My sample size is not greater than 30 here, right? It's small, it's 15, but if you take a second to plot out what the data looks like, there's no obvious skews or outliers. The data is kind of grouped, so there's nothing that you could say is definitely an outlier, and there's definitely skew, okay? All right, and just like the last one, for n, this is a paired t-test. Okay, so just like the last one, this is a paired t-test. Okay, and then I'm going to go ahead and calculate my test statistic. Okay, so that's my t step. Okay, so remember here we need lots of things. Okay, we need mu, which is 0. Remember, it's always the same as what you have up here. Okay, and then I'm going to get x bar from my calculator. Okay, and when I ran all of my data and did one variable statistics on it, I got negative 42.667, okay, which I will show you all right here. Okay, so here's my data, right? I entered all of the data and then ran the one variable statistics, and there's x bar and sx. Those are the 2 things that you need. Once you have those, you're golden. Don't need anything else. Okay, so x bar was negative 42.667. Then I need to calculate my new standard error. Okay, so my new standard error, remember, is the sx that they gave you. I need to rewrite that. That looks a mess. Let's try that one again. Okay, so my standard error, okay, is sx that you get from the calculator. So when I did this in the calculator, I got 84.0193 for sx, which makes sense because you have a lot of variation in this data. Okay, and then we're going to divide by the square root of n, which is 15 here. Okay, so when you plug all of that into a calculator, you get 21.6937. Okay, so that's my standard error. And the last thing I need is my degrees of freedom, okay, which remember, again, is always the sample size minus 1. So 15 minus 1 here, which is 14. Okay, you need that mostly because you need it for your calculator, right? So that the calculator can run the paired t-test for you. Okay, so finally I need to actually calculate my test statistic. Okay, so remember your test statistic is x bar minus mu divided by this new standard error right here, just like you would do with a z-score. Okay, so negative 42.667 divided, minus 0 divided by 21.6937. Okay, and when you work all of that out, you get negative 1.967. Okay, so that is my test statistic, right? It's like my boundary, okay, like my boundary on the normal curve. Okay, all right. So then my next step here is my O step. Okay, so remember with the O step, you have to write out what the actual, you have to write out the probability notation, right? So you can either write it with the difference, so probability that mu sub d, and this one is going to be less than negative 42.667, Okay, remember the value that goes in here is always X bar, right? Or the statistic value. We're trying to see how likely is it that I get another value that extreme or even more extreme if I did this again, if I ran this simulation again. So you can write it this way, or you can write it this way, okay, with the t, right, which is, that's why we calculate the t value. So the probability that t is less than negative 1.967. Okay, and again, if we kind of sketch out what this looks like, right? So here's my normal curve, there's my t, and I'm saying it's less than that. So I'm shading to the left. So t is going to be, when you plug it into your calculator, t is going to be your upper bound here. Okay, so let's do that. Okay, so I'm going to go back to my calculator, just my regular calculator. Okay, menu, statistics. Okay, and then before we do this whole thing, I want you to notice, see how it does say confidence intervals and stat tests here? Okay, so we've been doing confidence intervals and hypothesis tests by hand, right? Which you absolutely should do in order to get all of the points, right? Remember, I told you only about a quarter of the points on these tests, like doing the hypothesis tests and the inferences, comes from the actual math. Most of it comes from the assumptions. Okay, so typically you just have to write things out, and then the calculator will do a lot of the math for you. Okay, so I have a later video that I'm going to post for you guys that shows you how to run all of that, and it shows you exactly what, exactly what the calculator will show you. Okay, but for our purposes here, right, we're running, we're looking for TCDF, so that's distributions. TCDF. Remember, lower bound is going to stay the same. T is my upper bound this time, so it was negative 1.967, and my degrees of freedom was 15 minus 1, which was 14. Okay, so I'm going to go ahead and say okay, and there it is right there. So that is my p-value. That is the probability, that shaded region, the area under the curve. Okay, what we're saying is, in a lot of people missed this on the last test when they had to interpret p-value. So this value right here, the 0.034663, that is your p-value. If you're asked to interpret that, it's the probability of getting a sample value as extreme as the one you got, or even more extreme, right? How likely is it that that particular statistic or something more extreme would show up if you ran this simulation, right? Or did this experiment many, 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 many times. Okay. All right. So I'm going to go back over here, right? And I figured out what this value was. So it was 0.0346, which again, I realized I forgot to set an alpha value at the beginning, but that's less than any reasonable alpha value that we would set, because typically we set it at 0.05. Okay, so I'm not going to write the rest of this out because you have it over here to the left. Okay, so we're going to reject the null here because the p-value is less than alpha. And then there's my conclusion and context. So because the p-value is less than alpha, we're going to reject the null. And we say that there is enough evidence for HA, okay, which states that the true mean difference in supermarket lane checkout times is less than 0. So essentially what we're saying here is that, yes, we've proven with this test that the express lane is faster than the regular lane, right? Something you probably intuitively kind of understood, right? But now we actually have the math to back it up and to prove it, okay? So that's it for paired t-tests.